Testing a Keyestudio Relay Shield, a Spring City Solutions nodered project. This video shows electronic test results from tests done on a Keyestudio Relay Shield. You may also be interested in our two companion videos, how to set up a relay shield on a Raspberry Pi with Node-RED, and also how to use a relay shield with Node-RED. First, we'll examine the hardware, then some datasheet-based predictions, followed by test results from the LCR bridge, the insulation tester, the oscilloscope, spectrum analyzer. I skipped the vector network analyzer, it's not a microwave device. Then a summary of testing results and compared to the datasheet based predictions. Finally, if you're interested, you can donate to this project to fund future development of more drivers for Node-RED. First, the hardware. You could lay everything out on a table or in a shoebox. I made a little wooden half box to organize the parts. This case is 3 pieces of scrap exotic hardwood in an H shape with rubber feet on the top and bottom. The Pi and the other equipment hang underneath the top, so it can sit on my shelf, look nice, be protected from dust when it's right side up. Yet, when I flip it over, there's easy access to the Pi and to the wiring. It's hardwood, so I can drill and tap 440 size machine screws for mounting. Metric would work. Underneath the Keyestudio Relay board, I have a Pi-Juice battery system installed, so I have a completely wireless floating ground portable system. The power supply is from Amazon. It's a 12 volt to 3 amp USB microconverter with a standard amateur radio Anderson power pole DC input plug. You can buy very small diameter screws that easily fit through the Anderson power pole roll pin hole in the center of the connector. Something like a 2 by 56 thread will fit, and then add some nylon washers on top and bottom to space it off the board. Along the top of the board, there's a blue barrier strip. You can see the normally closed connector is to the left, the moving part to the middle, normally open connector to the right. The relays are numbered J5 through J2 in descending order along the top. Underneath the relays, there's LEDs that turn on when the relay turns on. Before I start testing, I'm going to make some datasheet-based performance predictions. The 4 relays on board are Songle Model SRD05VDC-SL-C. The lids of the relays specify 10 amps up to 250 volts AC or 30 volts DC. I found the manufacturer's datasheet for the relay. There's no data revision on the datasheet. The model number means the SRD series, 5-volt coil, sealed package, but it's not dustproof. Low coil power, which means 360 milliwatts for that series, and the C-type contact pinout with single-pole dual-throw connections. As for contact ratings, the datasheet lists 3 options, 7 amps, 10 amps, and 15 amps, which implies to me I own the 10 amp contact model. The datasheet provides no DC voltage switching limits, although the case implies interrupting up to 10 amps at 30 volts will not arc. The datasheet further claims safety approval ratings up to 3 amps at 125 volts AC inductive, aside from other claims. The datasheet claims contact resistance will remain below 1/10 of an ohm given 1 amp of 6-volt DC ceiling current for at least 10,000 operations. I have a calibrated LCR meter with 4-wire Kelvin test leads. I'm going to test that resistance. The datasheet claims 1,000 volts AC dielectric strength. I'm willing to test that up to 500 volts using an insulation tester. My tester always overvoltages a little in actual operation, so sending it to a kilovolt would test to, at least a kilovolt in 1/10, maybe more, which proves nothing if it fails. If it's good up to 500, it's probably good. The datasheet claims operate and release time are both under 10 milliseconds. I'm going to test that with my scope. The longest dimension on the entire relay is 19 millimeters. I'm going to predict usable RF performance up to 20 centimeter wavelength and excellent performance below 200 centimeters. I can and will test up to 1.5 gigahertz on the usual amateur radio frequency bands. I was curious how well the overall system would work for low-level signals, for example, switch and thermocouples. Also, are there any unusual or unanticipated capacitances or inductances when the contacts are open or closed? The datasheet claims contact resistance will remain under a tenth of 1 ohm for 10,000 operations. Let's try it. I connected the board to my LCR bridge in 4-wire Kelvin mode for testing, mostly by directly clamping onto the screw terminals on the top of the board. I did my testing on November 28th, 2021. The LCR bridge is a Matrix brand. It's a MCR 5100. It operates from 40 hertz to 100 kilohertz, although I did all my testing at 100 kilohertz. I have firmware version 1.8.1 and hardware version 1.1.1. A full, mostly automated closed and open calibration cycle only takes a couple minutes. The picture you're looking at shows the normally closed contact resistance of relay J2. On to the results. The good news about this LCR bridge and equipment is I can reliably measure resistances to at least 3 significant figures at the values encountered. However, at low resistances, the measured resistance depends strongly on test probe pressure. At reasonable handheld pressure, regardless of wiggling hands a little, I reliably measured about 4 hundredths of an ohm on all 8 closed contacts at the screw terminals. That's a bit less than half the relay datasheet's maximum specification, which is excellent performance. Measuring ultra small inductances is never fun nor easy, and I can't say my result is accurate to more than maybe one significant figure, but I did measure about 0.04 microhenry on every closed contact, which is about 40 nanohenries. If my calculations are correct, about 2 inches of 22 gauge generic bare connection wire has near exactly 50 nanohenries or so of inductance. So it seems totally realistic that a circuit board of the dimensions of an inch or two would measure about 40 nanohenries of inductance. If you're doing amateur radio antenna experiments, you could guesstimate that if you attach antenna wires to the screw terminals on the relay board, the board contacts add a little bit less than 2 inches of electrical length to an antenna element. So excellent performance, about what you'd expect. Capacitance measurements at those low levels were accurate to about 2 significant figures, depending on the exact position of my LCR probes. The measured capacitance could vary by about half of 1 puff or so, and my reported measurements are with the probes in the center of the top of the screw terminals. I found that very reliably the normally open contacts when open measure 3 puff almost exactly, and the normally closed contacts when open measure 2.6 puff. I'd attribute the difference in capacitance to some kind of internal hardware design, wire relay construction, something like that. It's very consistent. To give that some kind of useful application, consider the capacitive reactance of a 3 puff cap is about 1750 ohms at 30 megahertz, or almost exactly 50 ohms at 1 gigahertz. So, at least from a capacitance perspective, for amateur radio purposes, this relay board is a switch of pretty good isolation through HF bands and is more of a signal splitter than a signal switch at gigahertz frequencies. In all fairness, the datasheet markets this relay for no frequency higher than 60 hertz. Later in this video, we'll see some RF test results. I think a couple puff for a non-RF application relay and a small circuit board, it's realistic and reasonable. The relay is rated by the manufacturer to hot switch up to 250 volts AC and up to 30 volts of DC and withstand a kilovolt of AC across open contacts. I decided to risk connecting a relay to my insulation tester to measure leakage resistance across the normally open contacts. My insulation tester is a Peakmeter MS5205 digital insulation tester. It takes three hands to take a picture, hold the probes, and hold down the safety measurement button. So, this is merely a picture of the resistance of the normally open contacts on relay J2. The peak meter uses a 3 milliamp constant current source that sometimes overvolts by maybe 10%. So if I try testing to 1 kilovolt DC and the relay fails, all I've really proven is it fails at 10% over range. So I set the meter to 500 volts, which is still a ambitious amount of voltage for a Raspberry Pi to switch. I tested by physically touching the probes to the top of the screw terminals. Um, I'm not crazy. All the testing equipment, especially including the test leads, were all certified to at least Cat 3 standards. So I'm safe up to 600 volts DC, although I was only working up to 500 or so, which is yet another reason why I didn't want to test up to 1,000 volts. But I still think it's a valid test. And the insulation tester results, all 8 open contacts passed 500 volt insulation testing with resistances reading off scale high over 500 megohms, which is pretty impressive. I checked each open contact in regular resistance mode off scale high. Um, no damage or impairment was seen to the Raspberry Pi, no electrical discharges, no sparks or whatever. It easily works pretty well at 500 volts. As an example of a high impedance sensor, a stereotypical pH sensor has an output impedance around 100 megohms. I tested above that on my contacts, so I'd feel mostly okay about using those relays to switch between pH sensors. Subjectively, I have to say I was impressed to see Hobby Gear handle half a kilovolt with apparent ease. I connected the board to my oscilloscope to test contact bounce and switching time. I did my testing on November 29th, 2021. The scope's a dual channel, digital Rigol MSO 2102A, software version 000304 SP2, and hardware version 2.3. Let me try to explain my wiring. I tried to design my system to be wireless. It runs on batteries, connects to Wi Fi. It's ridiculously stereotypical that working on a wireless system involves a big mess of wires everywhere. What you're looking at here is channel one of the scope is connected via a handheld probe to the relay coil flyback diode. The scope's set to trigger around 2.5 volts. And note that the relay has an inverting driver with the coil connected to power. So channel one is inverted in the sense that the relay coil, when off, will show a voltage of 5 volts, and the relay coil, when on, would show a voltage of 0 volts because the relay driver pulls down to turn on the coil current flow. Meanwhile, channel 2 of the scope is connected to the moving connector or contact of the relay at the screw terminals. That's the one in the center. The normally closed contact is connected to negative, and the normally open contact is connected to positive of a Rigol DP832 triple digital power supply, and I set it to 5 volts. And the current's limited to 1/10 of an amp, although I'm sure it won't draw even that much. Note the external Rigol power supply is generating the voltages for channel 2, and that's floating. So if you connect the ground of the scope probe for channel 1 to the negative of the external supply, then you'll just get low current line noise. A lot of electronic lab bench work revolves around understanding what's at ground level, what's not at ground level, what's floating. Fixing isolated high voltage switching power supplies is particularly exciting. Anyway, here's the test results. So, what are we looking at in this oscilloscope trace? First of all, this is connected to relay J2 as I turn the relay from off to on. The top yellow trace is the voltage at the bottom of the relay coil. The other side is connected to 5 volts. The channel is set to 5 volts for division. So when it switches from the higher to lower, it's turning the relay coil on. Note that the scope is set to edge trigger on this channel at 2.5 volts. So that's how it ends up in the middle of the screen. The bottom blue trace is the voltage at the relay moving contact. Normally closed is connected to ground, normally open is connected to 5 volts. This channel is also set to 5 volts per division, so when it switches from the lower to the higher, the relay's contacts are turning on. The horizontal sweep on the scope is set to 1 millisecond per division. So, measuring from when the relay coil J2 is switched on to when the voltage at the contact stabilizes, I'd count that as about 4.9 divisions or about 4.9 milliseconds. The datasheet claims the relay will respond in less than 10 milliseconds all the time, so that's excellent performance. You can see some contact bounce when the relay turns on. From the first contact to settling down is about half a millisecond of contact bounce. It's interesting to compare the on to off performance. Note that relay J2 shuts off in only 2.9 milliseconds. Also, there's no contact bounce, it shuts off cleanly. Relay J3 switching from off to on, a little over 5 milliseconds, maybe a millisecond and a half of contact bounce. Relay J3 switching from on to off, 3.9 milliseconds, don't see any contact bounce. Relay J4 switching from off to on in about 5 milliseconds with half a millisecond of contact bounce. Relay J4 switching from on to off, about 4.2 milliseconds, no contact bounce. Relay J5 switching from off to on, 4.6 milliseconds, about a third of a millisecond of contact bounce. Finally, the last measurement, relay J5 switching from on to off, 4 milliseconds, no contact bounce. Measured performance far exceeds the datasheet's worst case specifications. Relay turn on time is about 2 milliseconds slower than turn off time. Takes from 4.5 milliseconds to about 6 milliseconds to turn on, and a bit less than 3 to perhaps 4.25 milliseconds to turn off. I didn't observe any contact bounce when turning off, uh, but when turning on, there can be up to 1.5 milliseconds of bounce. I would plan on worst case, probably 2. It's kind of surprising how the relay turns off faster than it turns on. Usually, the flyback protection diode forces the current in the coil to take longer to decay, so it's usually adding a protection diode makes it turn off slower than the turn on time. Maybe the relay's current limited when it turns on, making it very slow. Makes sense to prevent the Pi from rebooting due to a low voltage transient. Certainly it works well, doesn't really matter. Kind of interesting. I connected the board to my Spectrum analyzer to test RF switching performance on various amateur radio frequency bands. Did my testing on December 2nd, 2021. Spectrum analyzer is a Rigol DSA 815 with tracking generator option. Mainboard version 00.09, FPGA version 00.05, firmware 0.1.18, and boot version 0.1.4. It's old and needs a software upgrade, but it works fine. The red external reference that you see is a BG7TBL, that's Bravo Golf 7 Tango Bravo Lima, GPSDO. Kilo Echo 5 Foxtrot X-ray ran a comparison between this GPSDO, and which is only costs $100, and an HP cesium beam frequency standard, and they're competitive in terms of accuracy. So when I run tests, I'm probably frequency accurate to like a millihertz or something on the 23 centimeter band. I've always been a believer there's no point in doing things halfway. May as well use a GPS stabilized oscillator if I have one. What you're seeing in the picture is testing the isolation of relay J2, normally open contacts, while they're open, on the 6 meters amateur radio band. The wiring solid hookup wire about 1 inch long and BNC to alligator clip cables going from the spectrum analyzer tracking generator to the spectrum analyzer input. Yeah, I'm well aware this kind of wiring is not really acceptable at UHF bands and above, but as we'll see in the test results, how I connected the cabling wasn't really the limiting performance factor. I run my essay with a 20 dB attenuator kind of permanently installed on the input. You can correct for that attenuation by pushing the amplitude AMPT button, then changing the ref offset option to 20 dB. In theory, if I accidentally hook up a transmitter and transmit 10 watts into the spectrum analyzer input, that attenuated output would still be within the max input ratings, and transmitting much over 10 watts would probably melt the attenuator off the panel, thus saving the spectrum analyzer, at least optimistically. There's a trick to saving screenshots using the DSA 815. If you plug a modern 32 gigabyte flash stick into the slot, the software freezes up completely until it's removed. But if you can find a small, old 512 megabyte flash stick, that'll work fine if you reformat it as a FAT file system. Normally, you'd save everything except screenshots using the storage button on the 815. But to save screenshots, you press the printer icon. That's a dedicated hardware button on the far left side of the SA. Don't forget to configure the printer first to enable color and stuff. But it works. I'm only presenting results for Relay J2. The other relays performed basically identically within the precision limits of my equipment. Onto the spectrum analyzer results. This is a result of shorting the spectrum analyzer tracking generator alligator clips right to the spectrum analyzer input alligator clips with no normalization. Um, the assay is advanced enough that it can vary the output level of the tracking generator in real time, uh, and then you can short the input to the output, click on the tracking generator TG button, enable normalize option, and it'll zero out the effects of the cabling and provide a flat trace at 0 dB. So this is what my cheap hookup cables look like without normalization from 0 to 1.5 gigahertz. Frankly, smooth within 10 dB to a gig and a half. Not bad for a couple meters of RG58 and some cheap alligator clips, little hookup wire. Anyway, every time the sweep frequency was changed in all of the testing throughout the rest of this video, I would short and normalize the TG to obtain a compensated flat 0 dB across the full width of its sweep. So, in other words, after normalization, at the instant the SA is sweeping 750 megahertz, the TG would transmit at about plus 4 dBm instead of the desired average 0 dBm. So the net result is it would display a post-normalization flat line at 0 dB. Cool. Likewise, at the instant the SA is sweeping 1 gigahertz, the TG would have to transmit at about plus 12 dBm, whatever. A properly calibrated modern spectrum analyzer is pretty much like magic. This is sweeping a normalized tracking generator from 0 to 1.5 gigahertz on relay J2, normally closed contacts, and those contacts are closed. You could call this the full spectrum insertion loss if you were using the relay as a switch. It's not exactly a microwave relay. In fact, we're not going to bother with UHF and above testing. In all fairness, the manufacturer specs don't go much above 60 hertz. Sweeping from 0 to 1.5 gigahertz across normally open contacts, and those contacts are open. So you could call this the full spectrum isolation if you were using it as a switch. The traces look about the same, or at least similar at UHF and above. You can't see it in the graphs, but the insertion loss in the 2 meter frequency band was about zero point 0.2 dB across closed contacts, and isolation loss was about zero point 0.3 dB across open contacts. So above 100 megahertz or so, it's essentially a somewhat lossy and resonant piece of cable. So we're done with testing at VHF and above. Sweeping 50 to 54 megahertz, normally closed contacts, and those contacts are closed. You could call this the 6 meters relay off insertion loss. So, insertion loss runs around 1.7 dB across the 6 meter band. It's too high for a radio transmit receive switch. It might be tolerable for transmit receive switching for a low to medium performance transverter for microwave frequency bands. Sweeping from 50 to 54 megahertz, normally open contacts, and those contacts are open. You could call this the 6 meter band relay off isolation. I'm surprised to see more than 1 dB slope from the bottom to the top of the band, but 6 meters is wide, nearly 10% bandwidth. It's believable. The slightly better than 10 dB of isolation really isn't adequate for a transmit receive switch. A 5-watt QRP transmitter would drop half a watt into the receiver input. It's just too much. However, for something like the example of TX and RX switching for a low to medium performance transverter for microwave frequencies, it would be pretty good. It's better isolation than just using a splitter. Sweeping from 50 to 54 megahertz, normally open contacts. In this case, the contacts are closed because the relay's on. You could call this the 6 meter relay on insertion loss. Compare this slide to the first 6 meter slide. And this time the relay's on, and we're trying the other set of contacts. The scale's a little different, sorry, but the result is basically the same within about 0.2 of a decibel. It's nearing test equipment limits. Sweeping from 50 to 54 megahertz, normally closed contacts, and those contacts are open. You could call this the 6 meter relay on isolation performance. Again, you can compare this slide to the second 6 meter slide. And this time the relay's on, and we're trying the other set of contacts. And again, the result is the same within about 0.2 of a decibel, nearing test equipment limits. I'd say there's no point in further comparison testing of relays on or off. It's performance of the contacts is about the same at 6 meters and likely the same at lower frequencies. Sweeping 28 to 30 megahertz normally closed contacts, and those contacts are closed. You could call this 10 meters, relay off, insertion loss. At 10 meters, the insertion loss is dropping to a relatively smooth 1.4 dB, still kind of high for a transmit receive switch, but it's getting usable in low to medium performance applications. Sweeping 28 to 30 megahertz, normally open contacts, and those contacts are open. You could call this the 10 meters relay off isolation. At 10 meters, the isolation still varies with frequency, but is rapidly increasing to near 20 dB, which is getting usable for low to medium performance applications. Sweeping the high end of 24 megahertz, normally closed contacts, those contacts are closed, you could call this the 12-meter band insertion loss. At 12 meters, the insertion loss is dropping to a relatively smooth 1.4 dB, still kind of high, usable for low to medium performance applications. Sweeping the high end of 24 megahertz, normally open contacts, and those contacts are open, you could call this the 12-meter band isolation result. At 12 meters, the isolation is rapidly increasing to over 20 dB. It's starting to get very useful for medium performance applications. Sweeping the bottom half of 21 megahertz, normally closed contacts, and those contacts are closed. You could call this the 15 meters insertion loss. At 15 meters, the insertion loss is well below 1 dB. It's very usable now as a transmit receive relay for a low power transmitter or similar application. Sweeping the bottom half of 21 megahertz, normally open contacts, and those contacts are open. You could call this the 15-meter amateur radio band isolation. At 15 meters, the isolation is rapidly increasing to the upper 20s or so of decibels. It's very usable. I have a couple of conclusions about the RF performance of these relays. All the relays and all their contacts performed within about zero point 0.2 decibels of each other. What I'm getting at is there doesn't seem to be any point in trying to optimize by selecting one relay or one wiring configuration over the other. For example, there wouldn't be any point in using the normally open contact from relay J5 as opposed to normally closed contact on J4 or similar. I'll just wire it up as convenient. Above 2 meters or above 150 megahertz or so, it acts like a somewhat resonant bad piece of cable, regardless of relay contact position. Wouldn't really use it for anything above 150. From 6 meters or 50 megahertz down to the upper HF amateur radio bands, about 20 megahertz. It's usable for low performance applications, and on the 15-meter band, or from about 20 megahertz and below, it's really a surprisingly good RF relay. For a relay that was only specified up to 60 hertz, its lower HF band performance is remarkably good. Not doing vector network analyzer testing right now. As per the spectrum analyzer testing, the board seems to work best on lower HF bands, and the VNA I have access to works best on much higher frequencies. Based on the size of the parts in the relay, maybe it would make a good interdigital filter for the 47 gigahertz amateur radio band. Not really of practical use. I would predict the practical results would be similar to the spectrum analyzer test results. Keep it on or below the 15-meter amateur radio band, or best used below 20 megahertz. To summarize all of the testing results, the closed contact resistance and open contact impedance exceeded expectations, 0.04 ohms versus 500 megs. The capacitance and inductance were pretty much as expected and predicted, about 40 nanohenries and about 3 or so puff for capacitance. It passed the high voltage testing, passed 500 volts. Switch operations about twice as fast as specification. That's pretty good. Modest contact bounce goes away in a millisecond or two. It's not marketed as an RF switch and relay. It makes a fairly bad RF switch and relay from 20 to 50 megahertz, but it's surprisingly good below 20 megahertz. Overall, I'd give it a 5 out of 5 and a 10 out of 10. Please help fund the development of Node-RED related software by donating on the Spring City Solutions Node-RED project Patreon page. You can find a link on the Spring City Solutions Node-RED project page or scan the QR code. Here's a list of the topics covered in this video. If I ever have VNA test results, I'll edit this video to include them. If you need to contact us, this project has a dedicated email address at Spring City Solutions. It's nodred@springcitysolutions.com, or comment on our Patreon page. Raspberry Pi is a trademark of Raspberry Pi Trading. Keyestudio is a registered trademark of Shenzhen Keys DIY Robot Company Limited. Node-RED is a trademark or registered trademark of the OpenJS Foundation in the United States. This was a Spring City Solutions production, copyright 2021. Thanks for watching.